Yeah, hello everyone. And let me start by really thanking the organizers, for giving me the chance to be here. I learned a lot during this conference and also to be able to present some of the things we've been working on. This is obviously an expert audience, so I thought there's no need to have an introductory slide yet. Yes. So that Raphael is happy. I will still have a first slide before I start with the main part of my talk. And I thought it could be interesting, maybe it is, I hope, to tell you what initially got me interested in altermagnetism, right? So how I entered this. And the reason I entered it was actually because of the superconducting diode effect we had already been working on in a rather different context, I would say. And if you're not familiar, let me just briefly tell you. So it just refers to this situation where you have a superconductor and your critical current along some direction n is different along the critical current along some direction minus n, right? And here is an experiment which actually got us initially quite excited. There's some differential resistance as a function of current, and you can see here this is the superconductor, 0 is right here, so it's clearly asymmetric. And if you think about applying a current with a magnitude somewhere in this red region, you're going to get like 0 resistance in one and resistive behavior in the opposite direction. Now there's a lot going on in this also rather, I would say, interdisciplinary field. And in particular, I guess, the most commonly applied scenarios, you have a magnetic field, some spin-orbit coupling, and this, in many cases, if the symmetries are just right, is going to give you a diode effect of this form. Now, given by these amazing developments in the spintronics world with altermagnetism, we were just naturally thinking about this question a while ago, whether you can also have something like this where you place the magnetic field or spontaneous magnetization by something that has 0 net magnetization. Yeah? And, well, it doesn't work for an anti-ferromagnet because, well, you have time reverses symmetry times translation, and that's going to kill this effect, right? Because it's a macroscopic transport thing that you're looking at. But it turns out, and that's the question we basically asked in this paper, that altermagnets can do it. Even we made it as restrictive as possible when the superconductor is as boring as possible, in the sense I just wanted it to be a symmetric, BCS S-wave superconductor. But if you have the right point groups and the right altermagnetic order parameter, it turns out that you can get that.
You always need to break in.
You need to break in. Yeah. That's right.
Okay.
So you always need, spin-orbit coupling, or maybe you can now go with this anti-altermagnets, maybe eventually. But at the time, this was all pre-anti-altermagnet, so I'm going to be, using altermagnet. That's exactly right, and you will see this in this one example of a point group. So we classified this, but although we saw a lot of big tables, I'm not going to show that big table. I just want to pick one example. Right, 6V, and if you take an altermagnet, we use your notation of B2 minus, I believe, right, then you're going to get a diode effect. Yeah? Why is that? Well, if you look at the symmetries, of course, your system is invariant still under certain symmetries, and that's also important. So you have 3-fold rotation, reflection times time reversal, and 180-degree rotation times time reversal. And, well, if you think about those symmetries, none of those is going to kill your diode effect. And if you don't believe me, you can do some microscopic calculations. For many of these classes, we wrote down some minimal tight binding models and computed the critical current, which is actually a very interesting problem. But this is an introductory slide, so I'm not going to talk much about it unless Raphael wants me to.
No, I actually... Is there a direct connection between the size of the spin splitting and the size of the diode effect? Or in other words, if I want to maximize my diode effect, what should I look for?
It's a very non-trivial thing to get to the relation between the diode effect strength and the microscopic theory. Because it's like this very interesting trade-off between, you don't want to kill the superconductor too much, but you also want to make it sufficiently anisotropic. It is true, of course, by symmetry, of course, to leading order, if you expand the difference in altermagnetic order parameter and spin-orbit coupling, it has to be linear, but it becomes very quickly nonlinear. So, So it's not really trivial. Depends on a lot of details. All right. And by the way, it's also, I should say, it's not only about making this efficiency maximal. I would say it's very important that we also get finite critical currents, because
it's going way too fast.
That was I just wanted to flash some.
Okay.
Yeah.
That is okay.
Yeah. No, I'm going over that not through the calculation. Yes.
Conceptually,
Yeah.
So what's going on?
So you have a superconductor. You have an altermagnet with this B2 symmetry, and you compute the critical current, which I was about to say, but I got interrupted. Yes. And you compute the directional dependence of the critical current in the plane. I haven't said that because I was interrupted. right? And it looks like this, and you can see it's not isotropic, right? It's not even, right? So this direction and that direction, the critical current is different.
But would that happen even in the non-superconducting phase?
There is no critical current.
No critical current, but it still may say the conductivity.
The conductivity,
Would the linear conductivity be anisotropic?
Anisotropic for sure, yeah. Yeah, but we're talking about the superconductor, right? So this is a non-dissipative effect, right? Yeah, sure.
There's a question here.
Just to put this into context, so are you also looking at like a finite momentum pairing then? And this is where the inversion symmetry breaking comes in?
No. So here...
So what you're referring to is really to like Q equal to 0.
Give me a chance. Yeah. But to answer your question, right here, the point group symmetry already breaks the inversion symmetry. You can ask another question, whether you also allow for the superconductor to break it. We've also looked into finite momentum pairing. I also know that you did that too, and I was going to say that actually in just a minute. But just give me a chance, yeah?
Okay,
No, but it's good. It's true. Yeah. Say again. Oh, okay. All right. So this is the difference now, right? So I'm plotting the difference between positive and negative critical current, and you can see it's finite. That's all I wanted to point out. It also has some directional dependence, obviously. And just
I can come back to Paolo's question. So the linear conductivity cannot show this. This is not allowed in linear response, right?
Yeah, but again, I'm talking about the
I'm just asking that.
Yeah.
He's never going to finish his talk. He's really going to start the talk.
Yeah, thank you.
Let the speaker start the talk.
Yeah. All right. So I wanted to say that if you have those symmetries, you actually do get zero magnetization, as we all know here, right? If you just check, you can see that. And also, by the way, these zeros of this efficiency, this critical current anisotropy, they're pinned by these symmetries as well. So you can see this altermagnetic symmetry is reflected here too. So I also wanted to actually say exactly that because there's very nice other works. I'm excited that many other people are also working on this now, including your paper here, this first one, and where you also allow the superconductor to break symmetries. And there's also another paper by our chair, and maybe you will say something about this as well later. But this was actually just meant to tell you what initially got me excited about altermagnetism. Okay? All right. So let's really start with the talk. Yeah, as Eduardo said, right? So the first part was kind of motivated by this question, how can I make like a superconductor and an altermagnet like to pair simultaneously? Of course, you can just hope for it to happen in material. You can maybe sandwich it. All of this is very interesting. But we thought to play another game. Maybe we can convince a system that is already a superconductor, an unconventional superconductor, to become ultimately altermagnetic, and in the following way, namely using non-magnetic addatoms on the surface, right? And if we choose a superconductor that is unconventional, meaning that it has multiple, maybe competing order parameters, these magnetic addatoms might frustrate locally the physics and then lead to spontaneous symmetry breaking, which in this case, as we will see, can give us some altermagnetic non-trivial symmetries. Okay? And the second part, if I ever get there, is a bit more general, but it's very much connected to the first in the sense that it's also about disorder, right? But here, the question is, if I have random disorder, and I have a normal state that already has broken time reversal symmetry, let's say due to altermagnetism, of course, for the purpose of this talk here. And we really want to take into account the fact that these wave functions have multiple sublattices, so we have quantum geometric effects. And we'll see there's a very general connection between the disorder sensitivity and that. And of course, altermagnet is a wonderful example of this, which we will use as an example to illustrate it. Okay? So let's get started with this additive engineering superconductivity. So as a model, I like to use, I would call it minimal model, not toy model, right? We're not playing, as Raphael said. Yeah? It's not it's not a fully microscopic calculation, but let's just use a model that kind of like has all the characteristic features of an unconventional superconductor with some with some multiple competing states. And we're going to focus on the square lattice. There's a non-interacting Hamiltonian. So you can see here there's a nearest neighbor hopping T and next nearest neighbor hopping T prime. And we're going to take the impact of some possible spatial modulations via adatoms into account by local changes of the chemical potential and also changes of the hopping parameters. Okay, so that's the game I want to play. As interaction, we take some antiferromagnetic spin-spin. Yes. I just indicated it one. It's completely normal square lattice, cuprates kind of thing, right? Yeah. That's right. Okay, and superconductivity we'll study on the mean field level. So we do a decoupling in the singlet channel. And here this delta ij will be fully self-consistently computed, but I'm not assuming any kind of translation symmetry. I'm going to fully self-consistently compute this delta ij. And to give you some kind of like feeling for what you should expect, if we have the homogeneous case, so no W, no modulation of these hopping parameters, then for small mu, you're going to get your D-wave superconductor, which is kind of competing with an extended S-wave state.
What is your pairing mechanism here? I'm a bit confused. What is your interaction? Are you doing like a
this? So these are C dagger.
You're doing like a fake TJ model.
Fake TJ model. That's the way.
Yes. But there is no U-term.
There's no U-term here. Yeah.
There's no U at all.
No.
So that kind of implies there is a projection.
No,
Exactly.
there isn't actually.
Do you have projection?
No, he's just.
We don't.
It's just simply the bilinear.
Yeah, exactly.
That gives you the local spin condensation on the side I. Okay.
No. I didn't say that I do that, right? So, but I do exactly. Oops. Exactly this Hamilton. Yeah.
So there is no U.
There's no U. I mean, we can add one, but that's what we did.
But U is always there.
Yeah, sure. Yeah, it's true.
I mean, it's.
You can add a U, and
It's unavoidable. Okay.
I'm not sure it's going to change much about the extended S wave problem, but yeah.
Okay, I come from high to C.
Yeah.
It changes a lot. Okay.
Okay, yeah, but I mean, I think for the sake of that's what we did. That's how it happened. Low TC. Thank you.
Low TC.
Okay, but I mean, okay, maybe to justify it like this, there are other people who have studied exactly this Hamiltonian. It's a very nice paper. That was also one of our motivations. So this was studied to understand really cuprate physics, where it's disordered. We have one of the people in the audience, of course. And what they studied was random impurities and solved it also on the lattice. You see there's some variation of the order parameter for small impurity concentrations. If you have a lot of impurities, at some point you see that there's some red. It's a bit hard to see. If you zoom in and have good eyes, you can see that there are arrows, which refer to some kind of like spontaneous currents that are generated by this random disorder. And our motivation was to use this kind of like the fact that you get these loop currents, but do it in some well-controlled, modulated way, such that we can, get some, unique signatures, some clear signatures of loop currents with certain symmetries and analyze them. Okay, and I should say that, of course, there's a community of doing this adatom arrangement with STM. It's a very different system. It's mostly uncorrelated, but it's in principle possible to do these kind of things. And we wanted to see, push this a bit more in the direction of interacting physics by using, as I said, such an unconventional superconductor as a substrate. And here you can see a result from such a self-consistent calculation. So here red and black means there's different values of this W, this local potential. And the colors here on the bonds refer to the superconducting order parameter phase. And the thickness is the magnitude of delta. Okay, so the unit cell of this superlattice is 4x4 in this case. And let's analyze the symmetries. So we allowed superconductivity to break any symmetry, but it turns out it's the same in all of these superlattice unit cells. So translation is preserved, but you break time reversal symmetry, right?
So the blue bars.
Yes.
What? The blue bars are singlets, essentially.
I mean, locally you can decompose. I mean, everything has been.
You have this blue. I don't know. I want to understand the figure. Yeah. What are these blue bars?
Oh, these are the value. So you have this delta ij, as I defined here, which is the singlet component on a bond, right?
Oh, this is the amplitude. Okay.
Yeah, and I'm plotting in the thickness is the magnitude, the color is the phase.
Okay, so it's like a local singlet amplitude on that bond.
Yes, and of course it's modulates spatially, so it's also. I mean, you can. Yeah.
Should I be nervous about Anderson localization physics?
Anderson localization. I mean,
You were randomly.
Random.
it's not random. That's
It's
a
not
super.
random. Ah.
But I mean that, I think. I mean, it's even, I defined that's the unit cell, right? This was another.
So I don't need to worry about it.
I mean,
I'm not worried anymore.
way, I mean, there's some local physics that I'm taking into account. So I'm, yeah. Sorry.
Very nicely arranged.
Thank you. Okay, so this is, okay, we have broken time reversal symmetry, right? There are non-trivial phases you can check. It's reflection invariant here. You have some diagonal reflection times time reversal. You can check all of this, and the combination is, of course, 90-degree rotation times time reversal. Yeah? And I mean, in this audience, I don't have to tell you, right? You all immediately see the connection. These are kind of like typical altermagnetic symmetries, right? You would say B1G minus of D4H. Yeah? And it's important to point out that this is, of course, all spin singlet, right? These are all spin singlet amplitudes. So we don't have a spin altermagnet. It's all in the orbital channel, as far as I'm concerned so far, right? So you can think of it as some orbital altermagnetic superconductor, right? Because all of this comes from the superconductor. Okay, and okay, maybe you're interested in some observables that displays this. Well, you can compute the currents on the bonds, right? And you can see I'm plotting the currents here as arrows. Actually, only the largest one, so that the figure kind of makes sense. And you see that there are opposing chiralities of these loop currents. Maybe a better way to visualize it is to compute the magnetic field associated with it and show it in real space. And this maybe makes it more clear to you that we have this kind of like staggered pattern. But importantly, you know, this is the unit cell, so these are not related by translation. This blue and red, they're related by rotation.
I mean, in the high TC community, this is called the staggered flux model.
Okay, you can call it staggered flux, but this comes,
counter-propagating.
Yeah, I know. I mean, we've worked on loop currents, but that's intra-unit cell, right? Here, I'm sort of like enlarging it, right? And deliberately constructing.
But time reversal simply is not broken globally.
I mean, in the sense that I'm not sure. Okay, I don't want to go back to this.
No, it's not.
But I mean, these are the symmetries. Now you judge yourself, right? I would say, okay, whatever. Okay, I mean, you tell me. This is still there. It's up to you. Okay. All right. Just to see that this is a bit more generic, you can also use bond impurities and a larger superlattice cell, and you get the same physics. And I think here, personally, this looks even better, this magnetic pattern, because you see this local dressing of this magnetic field, which really, even if you forget about the superlattice, right, you kind of like see that it's really an altermagnet and not an antiferromagnet, right, because it's dressed locally. And maybe some of you say, well, it's not I really want spin altermagnetism, right? And you can get that, you just have to add spin-orbit coupling, right? Because if you do that, then this kind of like orbital broken time reversal symmetry and this staggered nature is translated to the spin channel, right? So here we are plotting, you take some BDG band and you're plotting the spin polarization on these constant energy surfaces, just picking some energy. And you can see this is the SX or spin X component. You see that there's some texture. It's actually odd, and so is the Y component. That's just because the in-plane component is because of C to Z like this. So it's actually just directly the spin-orbit coupling. But because of C to Z, the out-of-plane component has to be even. So this is where you see the altermagnetic, if you want, D-wave like splitting or texture of the spin, right? So this is clearly time reversal odd.
How did you include spin orb? Did you put now more orbitals or?
No, just nearest neighbor Rashba.
Just like a Kane-Malley kind of.
Or nearest neighbor Rashba. Yeah.
Breaking, okay.
Yeah. No. Yeah. This is why you can kind of like see it here, and this is sort of like the product of the two effects. Yeah. And you can look in real space. This is for 4x4 superlattice. This is just the superlattice unit cell, and you can see indeed you get some finite spin polarization with some interesting texture. And of course, by symmetry, if you check the symmetries, it has the same reflection symmetries as before, and it's clearly an altermagnet because of those symmetries, and it has zero magnetization as imposed by these symmetries. All right. So I hope this answers all of your questions. If you have more questions, Lucas is also here with a poster, so you can talk to him more, or to me, of course, after the talk. All right. So can I then come to the second part? Yep. Okay, so this is, so how am I doing? But I can get, I mean, we have a lot of questions, so that's included in the no? Okay. So I can talk for 15 more minutes, is it? Yeah. 10? Okay. But there's 15 minutes break
Yes.
of questions.
There will be questions.
Okay. Okay. I just keep going. All right. So this second part, as I said, is about we now have a normal state with already broken time reversal symmetry. Maybe you take, of course, an altermagnet, and you have a superconductor, and you ask the question, I have some kind of impurities with some concentration, and you ask the question, how stable is the superconductor against these impurities? But we really want to take into account this quantum geometric effects. Okay? That's a fancy word. Let me just, this is very frequently used right now in at least like the strongly correlated community and topology community. What it just means is that we take into account that there are Bloch states which have multiple components. In our case, it would be sublattices and spin possibly, or could be anything. And we take into account that these depend on k, right? These Bloch states. So phi of k, to be precise, is actually only the periodic part of those Bloch states in my notation here. And why do we associate some geometry with this? Well, you can define some kind of distance. You can just say, I define it like so between two Bloch states, which is 0 if they're identical, it's 1 if they're orthogonal. And then you can think of k and k prime being close and expand, right? Then you get this Gij, which is often called the quantum metric. Okay? And this quantity enters very naturally a lot of physical properties, maybe the superconducting energetics, just because the Bloch states and form factors matter, or superfluid stiffness. And one very well-known example is, of course, it enters how localized one-year states are, right? So one-year states are defined like so. You can relate them back to the Bloch states shown here. And of course, we're summing over k, right? So it really matters what the relative phases of this phi of k are at different k. And to fix that, right? So to fix this alpha of k, in this such a gauge transformation, one usually says I choose the one that maximizes or that makes these one-year states as localized as possible, typically with respect to some like variance of the position like so. And the quantum geometry now enters in the sense that there's a lower bound on this due to coming from or involving this quantum metric. Yeah? So you can see that somehow the k dependence of these guys kind of like constrains or gives you an obstruction to really localizing these objects in general. Right? Okay. And now the kind of question I want to ask here is, what is the role of this form of quantum geometry for disorder sensitivity in a superconductor? But as you will see, this is really important if time reversal symmetry is broken already in the normal state. Okay, this is a bit technical, but let me tell you at least one important point why time reversal symmetry is really essential to describe superconductivity. So let's say we want to do some low energy description, and we project onto the effective low energy degrees of freedom at some given k that are relevant for our superconductor. And let's say we have spin degenerate Fermi surfaces, just for concreteness. Then you would write down something like this to describe pairing. But if you do this a priori, that actually doesn't really mean much, because you have to tell me what kind of gauge you're using. Now, implicitly, we kind of like most of the time effectively use time reversal symmetry to just use this anti-unitary symmetry to relate the Bloch states at k and minus k, and then this gauge is fixed. And that's very convenient, this gauge choice, for many, many reasons. One reason is that in this very gauge choice, it holds that if you take a superconductor that with this gauge choice, it doesn't depend on k, then if you have just simple impurities that are delta-like, non-magnetic, you get that Tc is not affected by impurities unless you have localization, which I'm not explicitly excluding, because you only go to leading order and KFL, right? 1 over KFL. Yeah. All right. But of course, if time reversal symmetry is broken, you can't do this anymore. And intuitively, just to give you some intuition, you might think, sure, what I kind of like should expect is that the superconductor is somewhat unstable anyway, because I have even if I have locally non-magnetic impurities, they will be kind of like dressed by the Bloch states effectively at low energies so that they appear magnetic and pair breaking. But I really want to formalize this because I don't even know what I mean by delta of k, generically at least, without fixing the gauge. And of course, you can also have kinetic pair breaking, right? That k and minus k are not degenerate. So to address this, let me maybe start with some general formula of the suppression rate of Tc, which in this very general form we just recently derived. This paper will appear probably tomorrow on arXiv. where you can see here the disorder Tc as a function of this lifetime. And you can see to leading order n1 over t, you get this zeta, which defines some dimensionless sensitivity parameter. So Anderson theorem means it's 0, right? Famous example, unconventional superconductor would be 1/2 in my normalization, and Aprikosov-Gorkov parametric impurities would be 1. Just to give you the normalization convention. Maybe in the interest of time, I will skip this most general part. Let me just advertise it. Even including this kinetic pair breaking effect, you can write down a general expression for zeta. That looks a bit complicated, but really isn't. You can just plug in and get your zeta out of it. And one interesting thing, I want to just point out that if you have this kinetic pair breaking, this doesn't even have to be positive. It can also enhance Tc, actually. But let me maybe skip over the expression.
Can you just tell us a little bit what C and F are, just so we have an idea?
Yeah, I will just go to the important part.
Oh,
yeah,
okay.
just because I have to finish soon, right? Yes. So if let's say we remove the kinetic pair breaking, then this expression simplifies. Let's maybe focus on this case. So here, this W, right, is of course are these matrix elements of the microscopic form of the impurity with respect to the Bloch states. Okay, so this is where the quantum geometry is kind of like hidden, and this delta is simply my superconducting order parameter in whichever gauge you like, right? You can just fix that, and then everything is well defined in this equation. Okay. And now, okay, you can now say I pick a superconductor that care. Maybe I take the one that Marcel had in his talk, right? Plug it in and compute zeta. I want to take a different perspective. I want to say, let's say we are given some normal states, some quantum geometry, some impurities, and I want to ask the question, what is the best I can do? What is the best superconductor I can possibly have in terms of disorder sensitivity? Okay. And to be more precise, there are actually two perspectives on this, and the first one is a gauge perspective. Okay. So the idea is this. Let's say we fix some delta. Let's say, I mean, it's natural to say I fix a BCS kind of state. And I'm asking the question, which gauge should I choose that the BCS superconductor becomes most stable? Okay? That's the question. And if you look at this equation here, this is gauge invariant, the denominator, but the numerator isn't. So we kind of like want to minimize this object. Let's expand it out. There's a gauge invariant part, and there's a part that depends on the gauge. And since there's a minus sign, I want to maximize the orange box. Now, just as a comment, if I have time reverse symmetry, you can show that this optimization problem is always unfrustrated. And you can show that the maximum of this just cancels out I0, and I get back Anderson theorem, as I should. But this idea generalizes this to the case without time reverse symmetry. And without time reverse symmetry, this is generically frustrated. Okay? This problem. I will illustrate that in a second. But before we go there, let's take a look at a seemingly unrelated problem and then see that it's connected. Okay? And this is the following. Let's say we take our superconductor, whatever it is, and we compute the real space version of the superconducting order parameter. So x here is the distance, the vector that connects the two electrons that are paired. And alpha prime are just some internal coordinates. Maybe sublattice, maybe maybe spin or whatever you want. Can even be continuous. And then this is the expression. Okay. Now look at this. This is, of course, a matrix-valued complex thing, right? Let's simplify it a bit and look at just the real scalar measure. So I basically just take d dagger d with a trace. And I even insert some general v, which has to be Hermitian. But if you set v to be 1, then it's just the Frobenius norm of my Cooper pair wave function. Okay? And now let's take a look at the following. And that's the statement. Object. Let's take v to be my microscopic form of disorder. Could just be identity matrix, but I'm showing it for any form of disorder. Then it turns out that the intra-unit cell weight of the Cooper pair wave function is exactly the object I want to maximize. So what I've shown to you is that the maximization of the weight of the superconducting order parameter in the unit cell is the same as finding the most stable superconductor here. Okay? And if you look at this real space form, it's also very reminiscent of this Wannier state, Bloch state connection. The only difference being that we should think of this as some composite two-particle Bloch state. And so the statement becomes, if you have quantum geometry, in this case the time reversal odd part of quantum geometry, then this induces some quantum geometry of this composite Bloch states, which in turn give you an obstruction to localizing the Cooper pair wave function, which is the reason why the disordered problem is frustrated. Okay? That's the logic. So you can connect quantum geometry, obstruction to localization of a wave function by gauge choice to disorder sensitivity. All right? So say again?
It's the Barry curvature part.
I would say it's the real part more than the Berry curve. Well, it's yeah, with a okay, it's a combination of all of it. Yeah, because it's anyway, we should be a bit careful because it's kind of like anyway of this composite object. So, right. So you should think of these kind of composite Bloch states. Yeah. So in a way, to zeroth order, yes, but it's addressed also by the real part. So it's not only the Berry curvature. Okay, so that's that. Another perspective, just to say this, you want to maybe optimize just delta. That's almost equivalent. It's not exactly the same, but you will also see that it's generically frustrated. Okay? And so my statement is now a system has, if you want, this geometric form of pair breaking if there's no superconductor that can give you an Anderson theorem just because it's dressed by this kind of like Bloch wave functions that have non-trivial quantum geometry. And if I can have a few more minutes before, or do you, maybe can I just show an example that might clarify also? And then we can maybe go to questions because that's the last slide I have anyway. Okay, the best example, I think I had to pick this for this conference, right? We take the checkerboard altermagnet. No, not checkerboard? Okay. I call it checkerboard, sorry. Anyway, right, so I don't think this model needs explanation, right? So I have a nearest neighbor, next nearest neighbor hopping. I also include spin-orbit coupling because it's interesting in this context. We don't have to, but it's interesting here. And well, okay, so if I have that, then I'm splitting my Fermi surfaces, and I'm going to focus on k minus k pairing. You can also generalize that. That's motivated, of course, by the fact that if I'm in the weak coupling limit and I have somewhat an attractive interaction in this channel, then this is the only one with a Cooper log, so it will eventually be most favored, but you can also generalize this. And now, without going through the details, let me just show you the zeta optimal as a function of altermagnetism, yeah, and spin-orbit coupling on the other axis. All right. So first of all, you see that zeta is actually non-zero, so that means it's actually a frustrated optimization problem. Okay, so it's actually, you get this kind of pair breaking, and I'm using microscopically non-magnetic impurities, right? Nothing is magnetic microscopically. And you can see, first of all, if the altermagnetic order parameter is 0, I only have spin-orbit coupling, then I get 0 zeta optimal, as I should, because I'm back to kind of like time reversal symmetry. But of course, the more altermagnetism I include, the more pair breaking I get. And then you can play a game, maybe I'm just going quickly over this, of course, looking at that superconducting order parameter. That is optimal. It's kind of like an object, as you probably would have guessed, that has, so here I'm showing, that has both a real part in some gauge of my singlet component, that's what all I'm showing here, in orange on the Fermi surface, and in blue and red I'm showing the imaginary part, wherever it's positive or negative, and you can see that the best superconductor kind of like adjusts itself to the altermagnetic order parameter by following its symmetries, and there's actually a non-unitary triplet that is also there, which I have a hard time illustrating compactly here, so I'm just skipping it. And I should say that we also studied chiral normal states, that you could get very interesting superconductors, even topological superconductors to be the most stable superconductor, or spin triplet superconductors to be the most stable superconductors. That's not the case for this altermagnet here, sorry. But I should say, of course, it's something that is unique to the altermagnet and is not present in the antiferromagnet. And you can visualize this because if I turn off my next nearest neighbor couplings here, my altermagnet is secretly an antiferromagnet because it's just rotated by 45 degrees. And you can see this here. I'm plotting zeta optimal as a function of next nearest neighbor hopping, so this black hoppings here, as a function of phi. And you can see that this line down here just corresponds to the antiferromagnet, where I have this anti-unitary intra-unit cell symmetry, which actually guarantees me that there is an Anderson theorem, but only on this line. All right? So that's pretty much it. So these are like my students. You know, Sharon worked on this diet effect. Lucas is here. Dennis did most of the did the quantum geometry project. And I should also mention very briefly that there's also Jean is also here, with whom we worked a bit from a different direction on altermagnetism, more from the direction of quantum magnetism, where we asked the question, what are approximate spin liquids to altermagnet, what you would expect. And you can even generalize this to itinerant fractionalized altermagnets, where you can get, even though you have fully preserved spin rotation invariance, you can get an altermagnetic spin splitting of your spectral function in a unit cell due to fractionalization. If you want to know more about this, I'm happy to chat or talk to Jean in front of his poster. And that's it. Thank you.
Thank you for the talk. So like the figure there. So like at zero spin orbit coupling, your checkerboard Hamiltonian is real, right? But then you don't really have, you only have two gauge choices, +1 and -1.
At zero spin orbit. Oh, okay.
Right, because you have a PT symmetry, and then that's a reality constraint. But then, what does optimal? I mean, then the only gauges you can choose is plus or -1.
That's
right?
it. That's it. Okay, that's a very subtle. Okay, that's a bit subtle. So that's true. So there's another anti-unitary symmetry. So there's one thing I glossed over was the fact that now I have singly degenerate Fermi surfaces. We have also analyzed it for that case. All of what I told you go through with some extra comments. It turns out that if you do this, then along this line, where is it here? Along this line, that's what you're referring to. That's exactly right. There is a kind of like anti-unitary symmetry, but it's quest 2 +1. And since I'm spin non-degenerate, right? In that case, this naively without quantum geometry also you can show always gives you a zeta equals 1/2.
Yeah, but it looks like that the color changes.
Yeah, exactly. But that you only get exactly in this limit for infinite altermagnetic order parameter. And the reason why you get zeta optimal not equal to a half on this line, you can actually see just asymptotes to 1/2, is exactly because in this optimization problem, this omega of k comma k prime magnitude varies. And then it turns out that the order parameter to go up and down actually optimizes, gives you a better zeta than a zeta equals 1/2. So what you forgot is that the order parameter here, right, you can also vary in magnitude, which is what I'm also using. Okay?
Okay, and then maybe is this anyhow related?
So it was very technical, but that's a technical.
Yeah, no, I was just wondering, but we know that you can write the superfluid stiffness in terms of the quantum metric. Is this related? I mean, I don't know these equations well enough.
No, it's not really directly. I mean, of course, both of these two effects play a role in practice. I mean, for a physical system, but it's not really that story. I mean, it's of course. I mean, in the sense that, I mean, if you take a flat, or the stiffness, the statement about the stiffness is if you take a flat band, you might naively think that the stiffness is 0, but it turns out that there are these geometric contributions, and in some well-defined limit, you can show that it's basically the trace of this Gij I defined. But in my case, you can already see that it's, if at all, the kind of like quantum geometry even of a different object, which is this composite Bloch state. So it's not the same. It's spiritually related in some sense, I guess. But yeah.
Yeah, very interesting. So this reminds me of another story which is called superconducting fitness. Yes. And I was going to ask if you know links between what you do here and superconducting fitness.
Yes,
you do.
I do. So I can comment a bit on this, maybe. So the superconducting fitness, right, by Sigrist. So that's about the fitness of, like, you take some kind of pairing state and you ask how compatible is it, sort of like with a normal state Hamiltonian or and interactions, right? Yes. So here we are kind of like, if you look at this object, in the simplest case, this object over here in the denominator, you can think of this as somehow superconducting, if you want, I mean, fitness with respect to that given disorder potential. So that is really, but it's, that's basically the connection.
And so there were a couple groups that actually considered fitness in the context of disorder as well, and it looks similar in some sense. Yeah, so okay.
That's right.
Okay.
So we did, including us actually. Okay. So we were. So you're one of those groups. Yes. We can discuss a lot about this, but yeah.
I have two questions. One is maybe more philosophical or more. You showed how, if you break time reversal symmetry, how to properly define the gauge and so on. Now, what if I have, and this is something we were discussing yesterday about, breaking time reversal in different sectors. What if I have a P plus IP superconductor? I mean, I do break time reversal spontaneously. Do or not, yeah. But how do can I translate everything you did for the case when I have this as well? It's a multi-band and it's a relative phase that chooses whether I break time reversal or not.
Well, I mean, I would say a slightly different thing here, right? Because I'm talking about the gauge choice of my normal state Bloch.
Exactly, yeah.
And you're talking about the superconductor spontaneously breaking
Correct.
time reversal symmetry.
But shouldn't there be a connection? Because if my superconducting breaks time reversal, then the Bloch states.
No, the Bloch states are like with respect to the normal state Hamiltonian, they don't have delta. So one connection I can see though, okay, is if you take a normal state that has a chirality.
Right.
right, really is chiral, then it turns out that the most fit superconductor, if you want to use that language in a certain sense, that one is one that can have also itself a winding, although that depends on really parameters. But that's a connection you can see. You can have a scenario, right, where I have a normal state and that is chiral, and the most stable superconductor is a chiral superconductor.
Sure.
But that's not. That's more like you think of the superconductor kind of like cancel. So what happens in that case? If I can just go back to this question to give you some intuition. In that case, I kind of like have a winding in this object, and I kind of like try to make this also wind such that the combination is as non-winding as possible, given the constraints, of course, on top coming from the fact that I have fermions that pair, which must make this thing antisymmetric.
Okay.
So that's another constraint.
And the second question is, you calculated the suppression rate at infinitesimal disorder here, right?
We also did more actually in this paper, but I didn't show it.
But yeah, so that's my question. Because, for example, if you take an S-wave superconductor that is anisotropic, in the limit of a very strong disorder, TC flattens out and goes to... So can I relate that behavior also with the quantum geometry?
I guess so,
asymptotic behavior.
Yeah, I would. Okay, yeah, I guess so, right? If you have if multiples, it depends on the interactions. But let's say I have a lot of superconductors energetically not so far apart, then you could think of increasing disorder. And then, although you initially started with a superconductor that wasn't really so much compatible, you would eventually also get like another state. Let's say like one that the one that I just had. I know,
Based, there were all these discussions, right? So you can get, but can you relate that to the quantum geometry in the same way that you're doing here?
I guess so. Okay. That's yeah. So you can have, for instance, a scenario. Let's say you have a chiral state and a non-chiral state in this thing we discussed that are energetically close, but somehow the non-chiral state wins originally. Right. Then I increase disorder, and then I have a disorder-induced transition from a trivial superconductor to a topological superconductor, which is exactly one of the predictions of this. Yep, that's one way to phrase it.
So I think in the interest of time, we will thank the speaker.